Hello, I'm Tech. I'm presenting Socrates, System-on-Chip Resource Adaptive Scheduling using Deep Reinforcement Learning. How to design complex resource scheduling. Our goal is to design a scheduling algorithm that maps multiple tasks from hierarchical jobs to heterogeneous resources. We specifically design an SOC scheduling algorithm. As shown in the right, the top figure illustrates hierarchical jobs composed of multiple tasks, and the bottom figure shows the SOC board with heterogeneous resources or processing elements having different properties in task computation time and power or energy consumption. There is a plethora of research works for scheduling algorithms. However, classical heuristics hard to show optimal performance as increasing the system complexity. With the advances of deep RL or deep reinforcement learning, much research has shown outperformance over previous approaches. Existing neural scheduling algorithms mostly target a cluster environment that has different properties from an SOC simulation. Therefore, we develop a novel deep RL policy on SOC application. In this paper, we use DS3, a domain-specific system-on-chip simulation framework. It supports hierarchical workloads and heterogeneous processing elements such as memory, accelerator, and computing resources. The right figure illustrates two examples of the scheduling algorithm. Nodes and edges indicate tasks and communication delays in each incoming workload, respectively. Delays are additionally accrued when a simulation switches resources. Figure A greedily selects resources with minimum execution time, whereas Figure B selects resources aware of communication delays. Since B considers both resource performance and delays, it outperforms the greedy approach. There are several challenges for designing RL agent to SOC simulation. First, an overall performance depends on the scheduling policy mapping each task to which resources. There's stochasticity in heterogeneous resource selection. Moreover, since each job has a different task dependency, only tasks having no predecessors can be scheduled. An agent must handle a variable action set. Third, a simulation continuously injects indefinite jobs at high injection frequency. Lastly, our objective is to minimize average latency, which is dependent factors of total execution time and the number of completed jobs. Our scheduling model receives a varying number of tasks ready to be scheduled. We construct a state by concatenating interesting information such as the number of children tasked, job or task waiting time, and task statuses. Then, the model forwards its task iteratively to select one of the available resources. Here, the simulation paused until all tasks were scheduled. Afterward, the simulation continues with resources execution. Since tasks are completed by the scheduling order and performances of resources, the number of actions can be varied. A simulation computes reward, and the agent saved it to buffer accompanying state, action, and the clock signal at every task assignment. After completing a running episode, we proceed conventional algorithm. Here we use reinforced algorithm. When computing returns, we apply the eclectic interaction matching strategy. Conventionally, we have an experience collection with the form of state, action, reward, next state, denoted by SAR S prime. A reward is immediately followed before the next state is received. In this case of return computation, partial rewards are discarded because the states are concurrently received due to the task dependency. For our eclectic interaction matching strategy, we first store a pair of state action and reward signals separately. We track when completing actions and compute returns spanning each action duration separately in the backward pass. In that sense, individual returns are computed regarding the concurrently committed actions. We conduct experiments in different job injection frequencies. As indicated in the x-axis, higher frequency inject jobs much faster. We compare Socrates with the heuristic algorithms MET and HEFT, and neural algorithms DSOX and SCAR, which are developed for heterogeneous resource scheduling. The first two figures from the left show the overall performance of average latency and the number of completed jobs. Average latency is the total execution time over the number of completed jobs. As a result, Socrates surpasses other scheduling algorithms by a large margin. It has the lowest average latency and the largest number of completed jobs. We additionally report energy consumption on resources. Although we did not include energy components in the optimization and uses a default policy, Socrates still outperforms most other schedulers. In conclusion, we introduce a novel system-on-chip scheduler using deep reinforcement learning. The proposed algorithm uses an eclectic interaction matching strategy that rearranges experiences and computes returns spanning action duration. This simple technique addresses return mismatches arising from concurrently receiving observation by task dependency. Lastly, the proposed neural scheduler substantially outperforms other neural and heuristic schedulers for heterogeneous resources. For more information, please visit our paper. Thank you.